I think we were going to do one similar to this, but we'll do this one.
I think it was the part that was messing me up was the links connecting two nodes if their numbers differ by 3.
Okay, so we want consider a network having 7 nodes numbered 1 through 7, and the links connecting the 2 nodes are different by 3. So that means if we have a 1, then you would want to add or subtract 3. Well, subtracting 3 would make a negative value, so there wouldn't be 1 below it. But if we add 3, it can connect to a 4. And then 4 minus 3 is 1, or 4 plus 3 would give us the 7. And we're only using the numbers 1 through 7. So we've used the 1. It can only connect to 4. The 7, we could go 3 units back. 1, 2, 3, and get 4. Or we could go 3 units up, but then we're not including anything above 7. So again, 7 can only have 1, where 4 going up 3 is 7, going down 3 is 1. So we've used all of those. Any questions on that part? So I started with 1. I couldn't go down 3 because this is my lowest value, but I could go up 3. So that meant 1 connected to 4. 4 going down 3 is the 1 we already had. And going up 3 is the 7. So then I check the 7. 7 going down 3 is 4. Going up 3, we didn't go above 7, so there's nothing above it. And I'll start with the next one. This is going to have to have its own new link because none of these will connect with 2. So then if we have 2 going up 3, 1, 2, 3 gives us 5. We can't go down 3 because we don't use, that would have to be what, -1. There's nothing below 1. So 2 only connects with 5. So we did 2. Since I have 5, I'm going to check 5 next. From 5, going down 3, I get the 2, which I already have. Going up 3, I get to an 8, but we're not using 8. So we've done all the possibilities with 5. And then we go to 3. 3 going down, there's nothing there. Going up, 1, 2, 3, I get the 6. So 3 goes to 6. I went both ways with 3. Six going down 3, I have the 3. Going up 3, there's no value. So this is it. Any questions on it? Okay, so then we have, well, that would be our picture. So that would be part A. Is the network connected? So to be connected, you have to be able to go from each one of the nodes to every other one. Well, 1, 4, and 7 are connected. But from 1, 4, and 7, I can't get to this one or this one. So it is not connected. We have 3 components. What is the distance between node 1 and node 7? Now remember, your distance is always the shortest, but in this case, there is only one path from 1 to 7. It's 1, 4, 7. And so the distance is what?
2.
Because there's 2 links, or the number of nodes minus 1. Any questions on that?
So for part A, like the first part, where we have the 1, 4, 7, do we have to draw it like the first one? So do we have to draw it as like an L, or can we draw it as like a straight line?
It can be a straight line.
Okay.
And some students even had these in order, like 1, 2, 3, 4, 5, 6, 7. And that's fine, as long as only 2 and 5 is connected, and 3 and 6. So it could have been like that. And we know that 1 and 4 went together, and then 4 went to 7. And we know 2 and 5 went together, and 3 and 6. So it could have even been that way if you put them all in order first and then connected them. So they don't have to be straight lines, and they don't have to be in any order, as long as only 1, 4, and 7 are connected, and then 2 and 5, and then 3 and 6.
Okay, that makes sense.
I have another one. Let's see what's 3.1. That's at the end of this section. So let's just skip to that first. Let's try number 8. Because I thought we would do this first and then you do the homework, but either way, doesn't matter. So we're going to do the last problem first, problem 8. Because I think this is a nice problem to have on a test. But it says, consider a network having, again, it had 7 nodes. But in this case, the links can be different by 3 or 4.
Does that mean we get to decide whether or not they're going to be?
No, you want both then.
Oh.
Wait, it only went to 7, right?
Yeah.
It just kept counting. Okay, so you could think of the same process. Start with the 1. Now we can't go below, so we know that, but it can be a 3 or a 4. So go 3, 1, 2, 3. That means we're using the 4. Or 1, 2, 3, 4. So 1 should be connected with 4 and 5. Now you could put them anywhere staggered if you wanted to set them out like we did here first. you can do that. No, I know that's all my possibilities for 1. Now, if you want to do the ones you already have circled, that works. That's how I did it, but you don't have to. But go ahead and try, and then we'll go over it. But I want you to give a chance to try it. And this one should end up connected. So it should be one component rather than the 3 like we had in this one. If we start with 4, going down 3 gives us the 1. Going down 4 would be a 0. We don't have that. So going down, there's only the 1. 4 going up, 1, 2, 3 would be 7. So 4 has to connect to 7. And if we go up 4, it would be an 8, which we don't have. So those are the only possibilities for 4. If we go to 5, going down 1, 2, 3 is a 2. So 5 has to connect to 2. Going down 1, 2, 3, 4, it connects to 1. Which we already did. Going up, if we go up 3, it's an 8, 4 is a 9. Those numbers we're not using, so we've done everything with 5. And then I'm going to go to 7. 7 going down 1, 2, 3 is the 4, which we have. Going down 4 of them gives me the 3. Going up, I don't have anything above, so that's everything for 7. And then 2 or 3, whichever one. 2 going up 1, 2, 3 is the 5. And going up 4 is the 6. Can't go down because we didn't go further down to go 3 down or 4. So that's everything for 2. And then 3, notice going down doesn't work, but we could go up. 1, 2, 3 is 6. And 4 is 7, which I already have 3 with. Is that what everyone got? So it's just saying add or subtract 3 and 4 this time.
So you wouldn't draw 2 different things. You would just do it all in one.
Correct.
Okay.
Right, because they all ended up connecting. The other one didn't connect because of the values that went together. Because it could only be 3 each. They didn't, like 1, 4, and 7 wouldn't work with 2 and 5. But this one, because we added the difference of 4 in there, it connected them all. So then the network ended up being connected. So that would be part A. B is, well, I said it, the network is connected, so there's one component. What is the distance between node 1 and 3? Anyone?
Four.
1, 2, 3. Okay, well, it depends on which way we go. Notice we go this way, 1, 2, 3, 4. If we go the other way, 1, 2, 3. You want to take the shortest one. So anytime you're asked for distance, look at all the possible paths and then take the shortest one. So one path was going this way, which took 4. The other one is this way, which only took 3. So the distance, I'll just use D. Distance is 3. So always take the smaller one. Does the network exhibit triadic closure? To have triadic closure, your friends need to be friends. Notice 1 is friends with 4 and 5, but 4 and 5 are not friends, or there'd be a line here. So this does not have triadic closure. So in order to have triadic closure, everyone in the cluster has to be friends with everybody else. Which means there needs to be a direct link from each one to the other, because everyone's friend has to be friends. So we would have to have a direct link to all of them. Well, I don't have enough space to make them all. But one would have to connect to all of them and so on. But your friends have to be friends to be triadic. So if you had to explain it, you only need one to not work. One is neighbors with 4 and 5, but 4 and 5 are not neighbors. And that's why it is not triadic. Any questions on that part? I didn't want to use D because D they use for number of neighbors. Any questions so far? The last part, does the net, or I mean, what is the clustering coefficient? I don't have enough space to write this. Clustering coefficient is the number of actual links between neighbors divided by the number of possible links. Now there's a formula. I think we did that already. Yeah, it was right up here. So the formula for the number of possible links is here. You let D be the number of neighbors, and then you plug it into this formula, and that gives you the possible links. So if we look at any one node, notice it has 2 neighbors. 4 has 2 neighbors. 7 has 2 neighbors. They all have 2 neighbors. And that's why it said for any one of them, because they're all going to be the same. So D, for all of them, any one of them, they have 2 neighbors, each of them. Get rid of my dotted lines. So for the denominator, it's 1/2 D times D minus 1.
I thought. Never mind.
It's okay. Right here, it's the possible links is 1/2 D times D minus 1. Now you could also, possible links, they'd be linked to all of these, 1, 2, 3, 4, 5, 6. But it's 1/2 2 times 2 minus 1. Now, when you're finding this possible links, it doesn't mean the ones they can go to. It means from their neighbors, how many of them could be friends. Well, since he only has 2 neighbors, there's only one possibility. This one here. And that's why if you plug this in, you're getting 1. So the denominator is 1. This is 2 times 1 times 1/2 is 1. The actual, remember, it's how many of your friends are friends. Well, if we look at 1 for an example, it's friends with 4 and 5, but 4 and 5 are not friends. So actually, none of 1's friends are friends. The same thing, you can look at any one of these. If we look at 7, he has 2 friends, 4 and 3, but 4 and 3 are not friends. They are not connected directly. So they are all like that. If we look at 6, 6 is friends with 2 and 3, but 2 and 3 are not friends. And that's why it's 0. And that will work for all of this one because of the circle. So the clustering coefficient is 0. we have a network and it's connected, but clustering between them is 0. So it's how, you could think of it how strong your network is, how many links are within it. Well, this is the minimum. I guess not the minimum. We could actually pull one out and it would still all be connected. But we do have a circle. Any questions on that? Okay. The other one I didn't ask the clustering coefficient because it was so spread out that there wasn't really, because it wasn't connected, I didn't see a need for it. Any questions? Okay. Strong and weak ties, figure 10. Where'd it go? On page 136. This one shows strong and weak. The darker lines are the stronger, and then the thinner lines are the weaker. And it's important. Suppose that you're person A, so this person here, in the figure, and you're looking for a job. Which connection in the network is most likely to open up a new and different possibility for you? So if you work with these people in your inner circle that you always talk to, and they are all connected to each other pretty much, they probably all know the same people that you already know because they're in your strong connection. But you do have a link over here, maybe someone you don't see very often, but you do talk to. Notice they have a strong connection of other friends that you don't have. And so talking with them may get you more possibilities that you didn't know about than talking about this one. So having those weak links or looking for those will help you strengthen your connection or when you need to branch out. And the same thing goes when they're doing studies. These could be different states, and maybe this, I don't know, scientist is studying here, but he knows somebody in this network and he talks to them and then they can compare. And so by having those weak relationships, it's just someone you didn't see, but has a strong connection somewhere else that you can share ideas with or find a job. Any questions on that? Now, for the most part, if there is a weaker relationship, you would be told, and they haven't gotten into it yet, but sometimes there's weights on them. Like these ones, maybe this would only be a 0.2, but then these darker ones would be 0.8, that there's a stronger relationship. But I don't know if the book gets into that. It hasn't yet. They do have what's called a resilience. The resilience measure beta is given by this equation. Now, don't worry about the equation. We're going to see how to put it into a table, and it's a lot easier. I think it's a little confusing in this way. But A is the measure of the average strength. The sum of the degrees of all the nodes divided by the number of nodes, but I'll show you a table. H measures what the authors call the heterogeneity of the network. H is small. The nodes tend to be in the same or similar total degrees of strength. So this one, it would not be small because we have a lot of weaker links or thinner lines. The symmetry measure in a direct network, one in which the links have a direction or arrow, which these don't, S would have a value. But here's the steps. And there is on the homework tonight, you need to make a table and find this. So you make a table with 4 columns and as many rows as there are nodes. You put the names or labels on the nodes in column 1. In each row, column 2 lists the total strength. And the total, well, you could. In column 3, you list the total out strength going out. Finally, in column 4, list the product of the entries from 2 and 3. Product means to multiply them. So you just multiply across. Once this is done, you add up the 3 columns, 2, 3, and 4. And you divide column 4 divided by 2 or 3. 2 or 3 should have the exact same value, or you did something wrong. The resilience measure for a network can be computed in terms of total degrees or total strengths. It is made up of average node strength, symmetry, and heterogeneity measures. And it's just telling you how strong that cluster is or network. So if you look at page 139. This table. Notice they've already set it up. So it gave us the nodes. It gave us the in strength and the out strength. And notice 22, these match. And then multiplying across, 2 times 2 is 4. 4 times 4 is 16. 16. 3 times 3 is 9. You add these up, 74 and 22. So then to find the resilience, it would be 74 divided by 22. Which is approximately, I rounded 1 decimal place, 3.4. So once you set up the table, you just divide them. Any questions on that? That's everything from this section. Any questions on it? You think you can set up the table? Here, let's look at the problem. Okay, I think it's number 16. Okay, so for the homework, you're asked to do number 16. A network has, this is for today's. A network has 5 nodes, A, B, C, D, and E, and is complete. Every pair of nodes is linked. Each link has a strength possibility different in one direction from the strength in the other. The strength is listed in the table below. For instance, the link from A to B, so here A to B is 1. The link from B to A is 0.2. So going in goes this way, and you need to add across to get your ins and add down to get your outs. So when you're putting your table, the first thing you do is your node. And they are A through E. And then we have in, out, and I forget what they called the other one.
Is it product?
Right, you're going to multiply across. I think they call it strength, but it is the product.
No.
So in this one, going across, it has A, B, C, D, and E. Are those?
So what that means is A goes to B and it's 1. A goes to C and it's 0.8. So these are A going to each of them. So if you add across, it's telling you your total in. The other problem we looked at had already calculated the in and the out.
Oh, okay.
So adding across will get your ins. So if we go 1.8, 0.7, let's see, that's 1.5, 1.6, 2.6. So going across gets your ins, because this is A to B, A to C, A to D. So then B to A is 0.2, B to C, and so on. So it would be 7, 8, 9, 2.9. So you're just adding across. 5 plus 0.7 plus 0.4, 1.6.
I was just gonna get, if I didn't agree, you know how these guys have it there, we got the rest. Now, we got to find it more. So 33 is what fraction of 100.
Is that what everyone's getting? 1, 2, 2.4.
Wait, I have a question. So is it like the farther away, like the smaller the number, the weaker the link is?
The lower the value, the weaker the line.
Oh, okay.
So then Like A to B is strong, but B to A is a weaker link.
Oh, okay.
Now going out would be this way. So it'd be 0.2, 0.5, 5, 6, 7, 8, 9, 1.9. Now, one way you can check that you did them right, when you add down these two columns, the first two should match. If they don't match, then somewhere we added something wrong. Wait, I already added that one. Are they matching?
Yes.
Okay.
I'm serious. If I haven't thought about that in a while, that means close down the cell.
You can think of it as equilibrium because the amount in and out, even though between each node might not be equal, between the network it is. So like over here, A to B is not the same as B to A, but in the network they are. So for the out column, we just added down because this is going out. Because it would be B to A. So then going down is out. And then just multiply crossed. If I was going to put this on a test, unless it was the take home, but if I was going to put it on test, this table would already, at least the in and out would be given, and maybe you'd find the product. But I wouldn't have you do the whole thing. Rule of thumb, you should never, unless it's like a large decimal. You should never round until the very end. So when you add up the last column, are you getting 32.76? I added right. 4, 5, 6, 7, 8, 9, 10, 10, 20. So, 20, 22. Yeah. Then to find beta. Divide. I rounded my final answer 1 decimal place. Now it says in order for it to have resilience, beta should be greater than or equal to 6. So this network does not have very good resilience. So the network doesn't meet the threshold of being greater than or equal to 6. It's pretty far away from that. Any questions on that?
Wait, so the formula for beta is total in column 4 and total in column 2 or 3?
Right. So for column 1, you take, column 3, that would be this one, and you divide by either one of these. These two should match. So you add up the total, and then you take this one and divide by either one.
Oh, okay.
Any questions on that? No, well, let me move it. Okay. Under outlines used in class, which is where all the outlines I have for you are. I had also emailed it. You want to read this? We did the problem, so it's not. We'll start it next class, but I want you to read this before class. Because it was just a lot of, it's something you should read, and then we can just talk about it and go over it quickly. So I have like 3.2 what you should read, and then 3.2 the rest of the section where it'll have more formulas. But it's just like an explanation at first. So if you haven't already, read that for tomorrow. And then we will continue from there. Any questions?